Welcome to today's calculus lesson. In this session, we'll explore two concepts that often confuse students: the limit of a function and the evaluation of a function at C. The key question that we will address is the question that are these two always the same? In our exploration of calculus, we strive to understand how functions behave as their input approaches certain value, um, which is precisely the concept of limits. The limit at C represents the value that a function approaches as x gets arbitrarily close to a particular value. On the other hand, the function evaluated at C refers to the actual value of the function when we input the specific value C. It is the output of the function at that particular point, indicating its precise value on the graph. And as we have said earlier, they need not be the same. Throughout this lesson, we will carefully distinguish between these concepts. So let's dive into it. We earlier noted that the limit of f at c and the evaluation of f at c are generally not the same. Indeed, when these two do not coincide, four cases are possible. The first case happens when the limit of f at c exists, but f of c does not exist. Case 2, f of c exists, but limit of f at c does not exist. Case 3, both f of c and limit of f of c do not exist. And the last one, the fourth case, happens when the limit of f at c exists and f of c also exists, but they are not equal. Now, let us see. Consider this function. F of x equals x squared minus 1 over x minus 1. When the graph is sketched, it looks nothing but a line. In particular, the line with the equation y equals x plus 1. In fact, you could simplify the function at the left into we factor the numerator and cancel equals x plus 1. Or can you? Can we really simplify it that way? No, you cannot. When talking about function, cancellation is not allowed. Not unless you modify the domain of the function. Hence, we should take back this solution. The difference in their graph is this hole. The graph of f of x is punctured at x equals 1, meaning the graph has no value at x equals 1. So yes, that's another way of defining a function if we want it to be uh, not defined on a certain x value. Anyway, all of this simply means that f of 1 does not exist. How about the limit at x equals 1? Well, a visual inspection tells us that as x gets close to 1, the function gets close to 2. This in fact is the limit of the function at x equals 1. So we have a case where the function is not defined at a point, but its limit exists at that same point. And so they do not coincide. Let us now discuss a function where f of c exists, but the limit of f at c does not exist. This is the function that we considered in the previous video, and we found that it has no limit at 1. This non-existence of a limit is apparent when we look at its graph. Look at this. If you evaluate this function at 1, on the other hand, since 1 belongs to the upper subdomain, we evaluate it at x squared minus 2x plus 1. Hence, f of 1 exists. Case 3. Now let us look at the case where both f of c and the limit of f at c do not exist. Again, this was the function we considered before, and we found that it has no limit at x equals 0. And this is evident when you look at the graph. They are not meeting. If we evaluate this function at 0, obviously it's not going to exist because f of 0 equals 0 over 0, and 0 in the denominator simply means that the function is non-existent on that point. So the limit does not exist, as well as uh, f of 0 does not exist. All right. Case 4, both f of c exists and the limit of f at c exists but are not equal. So this is another piecewise defined function. The diagram here is its graph. It's a line actually, well, almost, since there is a hole in here. At x equals 1, f of 1 is kind of redefined up here, meaning f of 1 exists. On the other hand, we can see from the graph that the limit of this function at x equals 1 is 2, right? Hence, the limit of f at 1 exists. So these two exist. The function is defined at c. The limit exists at c, but they are not equal. All right. So we have seen different cases of a function whose limit at c and evaluation at c do not coincide. Although this part is not required in the study of calculus, it is good to have a good grasp of these differences, especially when we reach the topic of continuity.